So in the last lecture, we talked about two problems coming from the area of logistics that could be formulated as integer programs. We talked about the facility location problem, and we talked about the dynamic driver assignment problem. In this lecture, we're going to talk about one last third problem coming from the area of logistics that can be formulated as an integer program, and that problem is the traveling salesman problem. And as we talk about the integer programming formulation of the traveling salesman problem, we're going to learn about an interesting, cool modeling trick. And as we try to solve that formulation, we're also going to learn about a cool solution trick today. Okay, so our job today is to talk about the traveling salesman problem. What is the traveling salesman problem in English? Over a geographical region, we have a whole bunch of cities dispersed over this geographical region. We start from one of these cities, and we want to find a tour of the cities that visits every city exactly once and comes back to the city that we started with, such that the total length of the tour is going to be as small as possible. So that's what the traveling salesman problem is in English. Once again, we have a whole bunch of cities dispersed over a geographical region. We start from one of these cities, and we want to find a tour of these cities such that we visit every city exactly once and come back to the city that we start with, such that the total length of the tour is going to be as small as possible. So this is what the traveling salesman problem is. Okay, so let's try to draw a picture, see what this traveling sales problem looks like. We're talking about the traveling salesman problem. We have a whole bunch of cities dispersed over a geographical area. Okay. We start from one of these cities, and we want to find a tour of the cities that visits every city exactly once, such that the total length of the tour is going to be as small as possible. For example, a solution to traveling salesman problem could be like this. I start from here, visit this city next, and then I visit this city next, and then I go to this city, I go to this city, I go to this one, and then I go to this one, and then I go to this one, this one, this one, and over there. Okay, so that's what a traveling salesman tour could look like. Start one of the cities, visit each city exactly once, come back to the city that you start with, such that the total length of the tour is going to be as small as possible. So we're going to try to first write an integer programming formulation for the traveling salesman problem. Let's identify what the data for the problem is. The data for the problem is we have a whole bunch of cities. So let's say N is the set of cities we need to visit. And what else? We have the distances between the cities. So let's say C sub ij is the distance from city I to city j. Cij is the distance from city I to city j. Another way to look at the Cij number is I'm going to call it also sometimes as the distance of the arc ij. So there's going to be there's an arc between every pair of cities, and Cij is the distance on arc ij. So that's all the data. N is the set of cities that we need to visit, and Cij is the distance from city I to city j. That's the distance on arc ij. Good. What are the decision variables we need? So we're going to use only one decision variable. And our decision variable is going to be a binary decision variable. Let's call it xij. And the binary decision variable xij is going to take value 1 if arc ij is included in the tour. Xij takes value 1 if arc ij is included in the tour. Otherwise, xij takes value 0. Okay, so by binary decision variable xij takes value 1 if arc ij is included in the tour. Otherwise, xij takes value 0. In other words, xij takes value 1 if right after visiting city I visit city j. Xij is equal to 1 if arc ij is included in the tour. In other words, xij is equal to 1 if after visiting city I right after visit city j. Okay, so now we're ready to start writing an integer programming formulation for our traveling salesman problem. Let's start constructing an integer programming formulation. We're going to minimize the total length of the tour. Let's look at the arcs between every pair of cities. I is in the set of cities, j is in the set of cities. Let's look at the arcs between every pair of cities. Xij takes value 1 if we include arc ij in the tour. If arc ij is included in the tour, then we're traversing the length of that arc, and the length of that arc is Cij. So this is the total length of all the arcs that are included in the tour. So this is the total length of the tour that I'm trying to minimize. That is my objective function. Okay, Xij takes value 1 if arc ij is included in the tour. If arc ij is included in the tour, we're traversing its length. So this is the length of arc ij. So this is the total length of all the arcs that are included in the tour, which we're trying to minimize. So now let's try to think about what kind of constraints do we need to impose in a valid traveling salesman tour. Let's try to think about what kind of constraints we need to impose in a valid traveling salesman tour. Here's a valid traveling salesman tour that visits every city exactly once and comes back to the city that we started with. So in a valid traveling salesman tour, one constraint is that we leave every city exactly once. We leave this city exactly once, we leave this city exactly once, we leave this city exactly once, we leave this city exactly once. So in a valid traveling salesman tour, we need to impose that we're leaving every city exactly once. So that's one constraint that we need to impose. The other constraint that we need to impose also is that we need to enter every city exactly once. This city, we're entering it 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 exactly once. So in a valid traveling salesman tour, we need to leave every city exactly once. And also we need to enter every city exactly once. So we're going to write constraints that ensure that we leave every city exactly once, and we also enter every city exactly once. Let's take care of those constraints. Let's take a city I over here. I'm going to write a constraint that says we're going to leave every city I, we're going to leave every city I exactly once. We're going to write a constraint that says we're going to leave city I exactly once. From city I, we can go to city J, and the decision variable for that is xij. From city I, we can go to city K, and the decision variable for that is xik. From city I, we can go to city L, and the decision variable for that is x sub I L. So from CDI, I could leave to CDJ. From CDI, I could leave to CDK. From CDI, I could leave to CDL. And out of these options, I got to pick exactly one option because I'm leaving CDI exactly once, which means that XIJ plus XIK plus XIL, all added up has to be exactly equal to 1, which means that for a fixed I, sum of the XIJs has to be equal to 1. That's going to ensure that I'm going to be leaving CDI exactly once. So for a fixed I, sum of the xij's over all j's has to be equal to 1. So this ensures that I'm leaving CDI exactly once. And we have these constraints for every CDI in our network. So we're ensuring that we're leaving each city exactly once. So this is the constraint that says we're going to leave each city I exactly once. Likewise, we're going to write a constraint that ensures that we're going to enter each CDI exactly once. And here's what that constraint is going to look like. Here's my CDI. I can enter CDI from CDJ. And the decision variable for that is xji. I can enter CDI from CDK, and the decision variable for that is xki. I can enter CDI from CDL, and the decision variable for that is xli. I can enter CDI from CDJ, CDK, or CDL, and out of these options, I'm going to pick exactly one option because I'm going to enter CDI exactly once. So then xji plus xki plus xli, all of these things added up has to be equal to 1. So then for a fixed I, sum of the xji's added over all j has to be equal to 1. That is going to ensure that we're entering each city I exactly once. For a fixed I, sum of the xji's added over all j has to be equal to 1. This constraint ensures that we're going to enter city I exactly once. And we have this constraint for every city I. Okay. So now in our formulation, we're minimizing the total length of the tour while we ensure that we leave each CDI exactly once, and we also enter each CDI exactly once. Okay. And now let's try to think about if this formulation is enough to get a valid traveling sales motor. So now let's try to think about, is this formulation is enough to get a valid traveling sales motor? Okay. Let me try to draw you a picture. So let's try to draw a picture. Let's look at cities that look like this. City 1, City 3, City 4, City 2, 6, 7, and 5. Okay. Let's get a solution that looks something like this. From City 1, I go to City 3. From City 3, I go to City 4. From City 4, I go to City 1. And from City 2, I go to City 6. From 6, I go to 7. From 7, I go to 5. And from 5, I go to city 2. Okay, so let's look at a solution that looks like this. In this solution, are we leaving each city exactly once? We're leaving city 1 exactly once, we're leaving city 3 exactly once, we're leaving city 4 exactly once, we're leaving city 2 exactly once, 6 exactly once, 7 exactly once, 5 exactly once. So in this solution, we're leaving each city exactly once. Also in this solution, are we entering each city exactly once? We're entering city 3 exactly once, we're entering city 4 exactly once, we're entering city 1 exactly once, we're entering city 6, 7, 5, and 2 exactly once, so we're entering every city exactly once. So this is a solution where we're leaving each city exactly once, and we're also entering each city exactly once. But is this a valid traveling salesman tour? No, this is not a valid traveling salesman tour because this solution has subtours in it. We want to find one tour that visits every city exactly once and comes back to the city that we started with. This solution has subtours in it, so it's not a valid traveling salesman solution. Okay, so this is a solution where we enter every city exact once and where we leave every city exact once, but this solution is not a valid traveling salesman tour. So that means that enforcing these constraints, we're going to leave each city I exact once, and we're going to enter each city I exact once, is not enough to get a valid traveling salesman tour. So we need to write more constraints on our formulation that is going to ensure that we do not get any subtours to a solution to our formulation. Okay, so now we need to add more constraints into this formulation such that we never get a solution from this formulation that includes some subtours in it. So to be able to write the constraints that make sure that we do not get any subtours, let's try to mathematically understand what it means to have a subtour and what it means not to have a subtour. Here's a solution where we have a subtour in it. Let's also draw a solution where we don't have any subtours. Let me plot the same cities. 1, 3, 4 cities, 2, 6, 7, and 5. Let's draw a solution that does not have any subtours in it. Okay. Okay. So now let's try to understand why this solution has a subtour in it and why this solution does not have any subtour in it. Let's try to understand why this solution has a subtour in it and why this solution does not have any subtour in it. The solution on the left has a subtour in it because we can partition the cities into two partitions, namely the cities 1, 3, 4, and the remaining cities. The solution on the left has a subtour in it because we can partition the cities into two partitions such that there is no arc in the solution that connects a city from one side of the partition to a city on the other side of the partition. Let's say it again. The solution on the left has a subtour in it because we can partition the cities into two partitions such that there is no arc in the solution that connects a city from one side of the partition to the other side of the partition. Okay, this is why the solution has a subtour in it. On the other hand, the solution on the right does not have any subtour in it because no matter how we partition the cities, here's one partition, the solution on the right does not have any subtour in it because no matter how we partition the cities, there is always an arc in the solution that connects the city from one side of the partition to the other side of the partition. If you partition the cities in this way, there is this arc that connects the cities in one side of the partition to the other side of the partition, this arc. If you partition the cities like this, there is this arc that goes from one side of the partition to the other side of the partition, and you get the idea. Okay, good. So let's denote the partition of the cities as some set of cities S here, cities 1, 3, 4, and the remaining set of cities on the other side, the full set of cities minus S. And likewise, we're going to denote the partition over here again, some set of cities on one side and the remaining set of cities on the other side. Good. So then let's see it again. The solution on the left has subtours in it because we can partition the cities into S and the others such that there is no arc in the solution that connects the city in the set S to outside S. This solution over on the right-hand side does not have any subtours in it because no matter how we partition the cities, there's always an arc that connects the city from one side of the partition to the other side of the partition. Let's write that observation down. The solution on the left, has a subtour in it because we can partition the cities into into S and n minus s, such that there is no arc that connects a city in S to such that there is no arc that connects a city in S to another city in n minus s. The solution on the left has a subtour in it because we can partition the cities into S and n minus s such that there is no arc in the solution that connects a city in S to a city in n minus s. Okay. This is then what it means to have a subtour. This solution has a subtour in it because we can partition the cities into S and n minus s such that there is no arc in the solution that connects a city in S to a city in n minus s. This is what it means to have a subtour. On the other hand, the solution on the right-hand side does not have any subtour in it because for any partition of the cities into S and n minus s, there always exists an arc in the solution that connects the city from S to n minus s. So the solution on the right has no subtours in it. Solution on the right has no subtours in it because the solution on the right has no subtours in it because for any partition of the cities into S and S minus S, for any partition of the cities into S and n minus s, there is an arc in the solution that connects a city in S to a city in n minus s. Okay. So the solution on the right-hand side does not have any subtours in it because for any partition of the cities into S and n minus s, there always exists an arc in the solution that connects a city from one side of the partition to the other side of the partition. So that means that if you want to write a constraint that makes sure that we do not have any subtours, we're going to write the following constraints. So if we're going to write a constraint that makes sure that we do not have any subtours, we're going to write the following constraint. For all partitions of the cities into S and n minus s, the solution must have an arc that connects a city in S to a city in n minus s. So this is the constraint that we're going to write to make sure that we do not have any subtours. So to make sure that we do not have any subtours, here's the constraint we're going to write. For any partition of the cities into S and n minus s, the solution must have an arc that connects a city in S to a city in n minus s. So that's what we're going to write. To make sure that we do not have subtours, we will write the following constraint. We will write the constraint, let's say. To make sure that we don't have any subtours, we will write the following constraint. For all partitions, for any partition of the cities, for all partitions of cities into S and n minus s, there must be an arc that connects a city in S to a city in n minus s. For all partition of the cities into S and n minus s, the solution must have an arc that connects a city in S to a city in n minus s. So this is going to be the constraint that is going to make sure that we don't have any subtours. We do not have any subtours in our solution. Okay. So to make sure that we don't have any subtours, we're going to write a constraint that says the following: for all partitions of the cities into S and n minus s, the solution must have an arc that connects a city in S to a city in n minus s. Okay. This is going to make sure that we do not get any subtours. So let's try to write that constraint mathematically. Let's go back to our previous formulation and add that constraint in. Let's take a partition of the cities. Let's take a partition of the cities and the set of cities on one side of the partition is n, and the set of cities on the other side of the partition is n difference n. So we're going to write a constraint that says the following. For the partition of the cities into S and n minus S, let's look at the arcs that start from S and that end in n minus S. For any partition of the series into n and S and n minus S, for any partition of the series into S and n minus S, let's look at all the arcs, let's look at all the arcs, xij's, that start in S and that end in n minus S. So for out of all these arcs, we have to have at least one arc in the solution. So this sum has to be exactly equal to 1. So this says that for any, and we have this constraint for every subset of the series. For any partition of the series S, for any subset of the series that you pick to put on one side, there has to be an arc that connects a city in S to a city in outside S. Okay? So this is the constraint that says that for any partition of the series, for any subset of the series, for any partition of the series, for any subset of the series, in the solution we have to have an arc that connects a city in S to a city in n minus S. So these are all the arcs that connects a city in S to a city in n minus S. So we insist that out of all of these arcs, we're going to pick at least one in the solution. Okay, and our decision variables are binaries. Let's also write those. Good. So now this is the full formulation of the traveling salesman problem. Leave every city I exact once, enter every city I exact once. Moreover, make sure that there are no subtours. Moreover, make sure that for any partition of the cities into S and the others, the solution must have an arc to connect a city in S to a city outside the other, to a city on the other side of the partition. Okay. For any partition of the cities into S and the others, the solution must have an arc that connects a city in S to the other side of the partition, to a city in n minus S. Good. So this is the full formulation of the traveling salesman problem. So now let's think about this formulation. If I have n cities, I have a decision variable for every ij pair. So I have n squared decision variables. That's not bad. So if I have n cities, I have n of these constraints. I have n of these constraints. That is not bad. But look at these ones. Look at these constraints. So if I have n cities, I have one of these constraints for every subset of the cities. So if I have n cities, the number of constraints of this type I have is then 2 to the n. And the number of these constraints can get very huge very quickly. So for example, if we're looking at a problem with 10 cities that we need to visit, the number of constraints of this form is going to be 2 to the, if I have a problem with, let's say 100 cities, if I have a problem with 100 cities that I need to visit, then the number of constraints of this form is going to be 2 to the 100, and 2 to the 100 is a big number. So this is a formulation that was nice to write. But we have a bit of a problem when we try to solve this formulation because the number of decision variables are manageable. If you have 100 cities, you're going to have 100 times 100, 10,000 decision variables. We can deal with that. But the number of these types of constraints is going to be very large. It's going to be 2 to the 100 constraints of this form. So these are very, very large. So now the question is, how do I solve this formulation? So we're going to now learn a cool solution trick. How do I solve this formulation? So now let's think about how we can solve this formulation. So here's how we're going to solve this formulation. Here's how we're going to solve this formulation. First, we call these constraints as the subtour elimination constraints. Okay. So to solve this formulation, the first thing we're going to do is we're going to solve this formulation without any subtour elimination constraints, just like that. Okay. We solve this formulation without any subtour elimination constraints. And if we get lucky that the optimal solution to this problem without any subtour elimination constraints does not have any subtours in it, then we're good. Okay. So we solve this formulation without any subtour elimination constraints. We look at the optimal solution without any subtour elimination constraints. And if we get lucky that the optimal solution to this problem without any subtour elimination constraints in it, if we get lucky that the optimal solution to this problem without any subtour elimination constraints in it happens to have no subtours in it, then we got the optimal solution to the traveling salesman problem, then we're happy. But what is more likely to happen is that if you solve this problem without any subtour elimination constraints, you're going to have some subtours in your solution. Then we're going to add the subtour elimination constraints for the particular subtours that we see and solve this formulation one more time. Okay, and that solution may have subtours also in it. Then we're going to add the subtour elimination constraints for the subtours that we see in that solution and solve the problem one more time. And eventually, we're going to eliminate all the subtours and we're going to get to the optimal solution to the traveling salesman problem. So we're going to start by the formulation without any subtour elimination constraints, and gradually add the subtour elimination constraints to eliminate the subtours that we face along the way. So this is going to be the algorithmic strategy that we're going to follow. And let's now apply this algorithmic strategy on a practical example, on a numerical example. Let's see how this works, how this idea of adding the subtour elimination constraints gradually works. Okay, so let's apply this idea on a particular example. Here is the network that we're going to be looking at. So we're going to be looking at a problem with 10 cities. And this is the distance matrix between each pair of cities. For example, cities 1 and 10 are quite far from each other. The distance from city 1 and 10 is 11. But cities 6 and 7 are pretty close to each other. The distance from city 6 to city 7 is 1. And the distance cities, 3 and 5 are kind of intermediate distance from each other. The distance from city 3 to city 5 is 4. Okay, so this is the distance matrix between each pair of cities. I'm going to sort of exclude the diagonals because we cannot go from city I to I. So the diagonals are excluded in our distance matrix. So now let's try to find the optimal traveling salesman tour that is going to go over each one of these cities. That is going to go through each one of these cities and come back to the city that we started with. Okay. So I have a bit of a Python code to do that for us. So at the beginning, our decision variables are the number of cities. We have 10 cities, and we have the distance matrix. So I call that distance matrix as the cost matrix. Cost IIG is giving me the distance from city I to city J. Okay. And if you look at this distance matrix, it's pretty much the same matrix that we looked at on paper a second ago. One difference is that the zeroth row of this cost matrix is 0, because I just want to index my cities starting from 1 to 10 so that we have compatibility with the picture that we drew. So all of our cities are going to be indexed from 1 to 10. And likewise, the first column of this cost matrix is 0. So the 0th column of this cost matrix is 0. So again, that ensures that I'm indexing all of my cities from 1 to 10. Okay. So the 0th row and the 0th column of this cost matrix are excluded because again, I want to index my cities starting from 1 to 10. And if you again compare this cost matrix, let me put it this way, with the cost matrix that we had on paper, it is the same numbers. They're the same numbers. We have 7, 4, 6, 9, 7. We have here 7, 4, 6, 9, 4, 7, 4, 6, 9, 7, 8, 9, 9, 11. It's the same numbers. Like if you check the last row, it's going to be 11, 7, 7, 4, 4, 4, 4, 2, 1. So they all match. Here in diagonals, I put hundreds. So that's going to make sure that we never go from city I to city I. So here in the diagonals, we put all hundreds. And there are a little bit of deviations here. So for example, the distance from city 2 to city 3 is given as 4. Here I put it as 3.99. And likewise, the distance from city 5 to city 2 is, I'm sorry, what is this distance? This is the distance from city 5 to city 2 is, 3 here. But I put 2.99 here. And the only reason we did that is there is multiple optimal solutions to this traveling salesman problem. Just to make sure that the solution that we get matches to the solution in the course packet, I perturb the costs a little bit just so that we get the same solution that is written in your course packet. Okay, we don't hit the alternative optimal solutions here. Good. So this is essentially the same cost matrix that we have on paper with very small perturbations. 3 has been perturbed to 2.9 here. 4 has been perturbed to 3.99 here. Maybe another 3 over here has been perturbed to 2.99 here, but very little minor perturbations. Okay, so this is our data. We have the cities and we have the cost matrix. So now let's write down the integer programming formulation. Let's write down the integer programming formulation that implements the model with the objective function, with all of the constraints other than the subtour elimination constraints. Okay, so let's write down the model with the objective function. We're going to leave every city exactly once. We're going to enter every city exactly once, but leave out the subtour elimination constraints, without the subtour elimination constraints. So let's write down this much of the model. Good. I create an empty integer programming model. This x vars variable is a 2-dimensional array, and the ijth entry of this array is going to include the decision variable xij. So then I loop over every ij pair. And when I'm loop overing I and j's, I'm looping from 1 to 10 with a skip of 1. So this makes sure that my cities are again indexed from 1 to 10 as opposed to from 0 to 9. So I loop over every ij pair. For every ij pair, we create a variable. The type of that variable is binary. So now we see how to define binary variables in Groby. And the name of that variable is xij. Okay, and we add that variable to our model. And as soon as we add that variable into our model, we also add that variable into our xvars array. So now the ij entry of my xvars array keep track of the decision variable xij. Okay, so this creates all the decision variables xij's that we had in our model. And this, again, this two-dimensional array xvars is keeping track of the decision variable xij. Now that we create all these decision variables, let's update our model so that all these decision variables are properly registered. The next thing we do is we create the objective function of our model. We create an empty linear expression. So it's going to keep track of our objective function. For every ij pair, into our objective function, we add the term cij times xij. So now by the time we get out of this double loop, we constructed the objective expression, cij times xij is all added all up. So then we set the model's objective function as our objective expression, and we're minimizing the objective function. So now we set the objective function. Next, we're going to write a constraint that makes sure that we leave every city exactly once. We're going to write a constraint that makes sure that we leave every city exactly once. What is that constraint going to look like? For every city I, we're going to write a constraint. For every city I, we're going to write a constraint. In the constraint that we write for city I, we're going to add up all of the xij's over all j and set it equal to 1. For every city I, we're going to write a constraint. In the constraint that we write for city I, and for every city I, we're going to write a constraint. In the constraint that we write for city I, we're going to add all the xij variables over every j and set it equal to 1. Let's write those constraints. For every city I, I'm writing a constraint. So now I'm writing a constraint for CDI. Let's construct an empty linear expression that's going to keep track of the left-hand side of the constraint for CDI. In the left-hand side of the constraint for CDI, we're going to add up all the xij variables. So loop over j, left-hand side of the constraint for CDI is adding up all the decision variables xij's over every j. So this is the left-hand side of the constraint for CDI. Then we add the constraint for CDI into our integer programming formulation. The left-hand side of the constraint is this linear expression that we created. The sense of the constraint is an equality constraint. The right-hand side of the constraint is 1. And we also give a name for the constraint. This is the constraint that ensures that we leave CDI exactly once. So we call that constraint as out I. So this is the constraint that ensures that I get out of the CDI exactly once. And likewise, we're going to write a constraint that ensures that we enter each city exactly once. If you want to write a constraint that ensures that we enter each CDI exactly once, here's what we're going to do. For every CDI, we're going to write this constraint. We enter each city exact once. In the constraint for CDI, take the xji by xji variables, add it over all j. In the constraint for CDI, take the xji variables, add it over all j. Here we go. For every CDI, we're going to write one constraint. So I'm looping over every CDI. And here's the constraint I'm writing for CDI. Create an empty linear expression that's going to keep track of the left-hand side of the constraint. So in the constraint for CDI, take all the xji decision variables. So this is xvars ji. Take all the xji decision variables, add it all up. That is the constraint expression for the left-hand side of the constraint for the ith city. So now for the ith city, we're adding a constraint into our model. The left-hand side of the constraint is this linear expression that we constructed. The constraint is the equality constraint. The right-hand side is 1. And the name of the constraint is in I. It means that I'm getting into each city. This is a constraint that says that we're getting into each city I exactly once. And now let's update our model to make sure that our objective function, the two sets of constraints are properly registered. And let's write our model into a text file called tsp.lp, just to make sure that we do not make a mistake when we're implementing our model. So then with the work that we did so far, we implemented our integer programming formulation. We implemented our integer programming formulation this much. Objective function, we're leaving each CDI exact once, we're entering each CDI exact once, and our decision variables are binary. We do not write anything about these subtree constraints just yet. Okay, good. So let's go ahead and run this formulation and see what kind of an LP file we generate. Run the traveling salesman example formulation. Okay, finish with exit code, no complaints. There is a tsp.lp file. Let's look at what this LP file looks like. In the objective function, we're taking all the xij pairs, multiplying them with the proper distances, add it all up. So let's not worry about the numbers in the objective function. That looks correct. But let's inspect the constraints. Let's inspect the constraints. Here are the constraints that says we're going to leave each city I exactly once. So let's check one of these constraints. Like, for example, let's check this one. We're going to leave city 4 exactly once. From city 4, we can go to city 2, 1. From city 4, we can go to city 2. From city 4, we can go to city 3. From city 4, we can go to city 4. From city 4, we can go to city 5. City 6, city 7, city 8, city 9, city 10, all of these sums are adding up to 1. So this indeed ensures that we're going to leave city 4 exactly once. Okay. Let's also look at the constraints that ensure that we enter each city I exactly once. Here are those constraints, these in constraints. Let's again pick one of them. Let's pick city 7. Into city 7, I can come from city 1, x17. Into city 7, I can come from city 2. In city 7, I can come from city 6. Into city 7, I can come from city 9. From city 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These are all the possible cities I can go into city 7 from, and they are adding up to 1. So the in constraints are also properly implemented. And then lastly, at the very end, we have this binary section. This ensures that all the xij variables are going to take binary values. And it's the kind of section that we haven't seen in our other formulations before. If you have binary decision variables, you have to specify them in a binary section. Okay, so this is again the LP for this is the integer programming formulation of R. This is the integer programming formulation of R in traveling salesman problem without the subtree elimination constraints. Let's go ahead and solve this formulation. My model dot optimize. And now let's look at the solution. My model dot print attribute. Let's write the print attribute on the screen. So it's going to print the optimal solution to our integer program without any subtree elimination constraints. Okay. So let's run this file, traveling salesman example.py. Let's run this file. Okay. We solved the model, and this is the solution that we got. Let's look at the solution that we get without any subtree elimination constraints. Let's plot the solution that we get without any subtree elimination constraints. Okay. Let's plot the solution that we get without any subtree elimination constraints. Good. According to the optimum values of my decision variables, x13 is equal to 1, which means that I'm going city from 1 to 3. x24 is equal to 1, which means that I'm going from city 2 to city 4. x31 is equal to 1, which means that I'm going from city 3 to city 1. x48 is equal to 1, which means that I'm going from city 4 to city 8. x52 is equal to 1, which means that I'm going from city 5 to city 2. x67 is equal to 1. x76 is equal to 1. x85 is equal to 1. x910 is equal to 1. And x109 is equal to 1. Okay. This is the solution that we get when we did not impose any subtree elimination constraints. So this is the solution that we got when we did not impose any subtree elimination constraints. Do we have any subtours in the solution? Yes, we have 1, 2, 3, 4 subtours. So now we're going to add the subtree elimination constraints for these 4 subtours that we've seen. Okay, so this solution that we obtained without imposing any subtour elimination constraints has subtours in it. We have 1 subtour, 2, 3, 4 subtours. So now we're going to add the subtour elimination constraints for these subtours that we're seeing. In particular, let's look at this subtour, subtour 1,3. We have this subtour 1,3. We have this subtour 1,3 because we can partition the cities into 1,3 on one side and all the other guys on the other side, such that there is no arc in the solution that connects the city from this side to this side. So now our subtour elimination constraint is going to say, in your solution, you have to have an arc that connects the city from this side of the partition to this side of the partition. Okay, so in the subtour elimination constraint we're going to add a constraint that says in our solution we have to have an arc that connects the city from this side of the partition to this side of the partition. So let's write that constraint. So we're writing the subtour elimination constraint for the subtour for the partition of the cities 1 and 3. Let's write that subtour elimination constraint. So we're going to write a constraint that says in the solution we have to have an arc that connects the city from this side of the partition to this side of the partition. So what are the arcs that connects the city from this side of the partition to this side of the partition? What are the arcs that connects the city from this side of the partition to this side of the partition? That is x12. What else? x14. What else? x15. What else? x16. What else? x17. What else? x18. x19, x110. These are the arcs that connects the city from this side of partition to this side of partition. What else? x3, 2. Let me write it over here. x3, 4. x3, 5. x3, 6. x3, 7. x3, 8. x3, 10. x3, 9. x3, 10. These are the arcs that connects the city from this side of the partition to this side of the partition. Among all of these arcs, we have to select at least one in a solution. This is the subtour elimination constraint that is going to make sure that this subtour does not happen. Make sense? Good. 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 So now we're going to add this constraint into our integer programming formulation. And we're also going to add the subtour elimination constraint for this one. We're going to add the subtour elimination for this one and for this one as well. So let's go ahead and add this subtour elimination constraint. In order to methodically add the subtour elimination constraint, here's what we're going to do. We're going to take this partition of the cities 1, 3, and we're going to look at every arc in our network, If the arc is beginning in 1 or 3 and ending in outside 1 or 3, that arc has to appear in this constraint. Let's see it again. To add this subtour elimination constraint methodically in our Python code, here's what we're going to do. We're going to take this partition of the cities 1, 3, and for every arc, if the arc starts from 1 or 3 and ends in outside 1 and 3, that's an arc that needs to be included in this constraint. Okay? So then here's how we're going to eliminate the subtour elimination constraints. Here's how we're going to implement the subtour elimination constraints into our integer programming formulation. So let's take a tuple. Let's call that partition. And that tuple is 1, 3. Okay. And now we're going to loop over every possible arc for I in range 1 to number of cities plus 1 and 1. For j in range 1 to number of cities plus 1 with a step of 1. So now look at arc ij, look at arc xij. If I is starting one of the cities 1 and 3 and j is ending outside the cities 1 and 3, this is an arc that goes from the partition on the left-hand side to the partition on the right-hand side. This arc has to be included in the subtour elimination constraint. So then if I is in the partition and j is not in the partition being this tuple, then this is an arc that needs to be included in our subtour elimination constraint. Good. So let's open a linear expression. Let's call that constraint expression. That's going to keep track of the left-hand side of our subtour elimination constraint. So if I is in the partition and j is outside the partition, if I is in the partition and j is outside the partition, then we're going to add the decision variable xij into this constraint. So this is a nice, again, systematic way to construct the left-hand side of our subtour elimination constraints. Let's come back over here. So now I'm writing the subtour elimination constraints for the partition 1, 3, and others. We're looking at every possible arc. And if the beginning point of the arc is one of the cities 1, 3, and if ending point of the arc is one of the other cities, then this is an arc that needs to be included in this subtour elimination constraint. Great. So then we constructed the left-hand side of the subtour elimination constraint. So then add this constraint into our model. My model dot add constraint. The left-hand side of the constraint is the constraint expression that we constructed. The sense of the constraint is greater or equal to, and the right-hand side is 1. The sense of the constraint is rho b dot greater or equal to. Right-hand side of the constraint is 1. Let's give a name to the constraint. So this is the subtotal elimination constraint for the partition 1, 3. Good. So now let's try to run our code without even solving the optimization model, just to ensure that our implementation of the subtotal elimination constraint is correct. Next parentheses here. Okay. Let's run this code to make sure that our implementation of the subtotal elimination constraint is correct. We're printing our model into this file tsp.lp. Let's see what it looks like. Run traveling salesman example. Let's look at the text file. Again, the constraints out, ins, those constraints are the same. I'm more interested in the subtotal elimination constraint that is right over here. Here we are. It's a good way to do this. Up. What is a good way to do this? Here we are. Maybe it's hard to see both things, but let's see. The arcs that go from 1 to 3, 1 to 4, 1 to 5, 1 to 6. So 2, 4, 5, 6, 7, 8, 9, 10 from 1. 2, 4, 5, 6, 7, 8, 9, 10. And likewise, let's come back here. The arcs that are going out of 3, 4, the arcs that are going out of 3, 2, 4, 5, 6, 7, 3, 8, 9. 2, 4, 5, 6, 7, 8, 9, 10. Okay, let's go back here. 2, 4, 5, 6, 7, 8, 9, 10. So it's exactly what we needed. So this subtotal elimination constraint is properly implemented. But now we're going to add the subtotal elimination constraint for every subtours that we're seeing. For all the subtours that we're seeing, let's write down the subtotal elimination constraint for another subtour. For example, we have this subtour. We have this subtour because we can partition the series into 2 partitions. 2, 4, 5, 8, and the other series, such that there is no arc in the solution that connects the city from this side of the partition to the other side of the partition. Good. So now we're going to write the subtour elimination constraints for the subtour that includes the partition that is involved with the partition 2, 4, 5, 8. So let's look at the. Let's write in a different color. That's nice. 2, 4, 5, 2, 4, 5, 8. So now we're going to write a constraint that says, in the solution, we have to have an arc that connects the city from this side of the partition to this side of the partition. In the solution, we have to have an arc that connects the city from this side of the partition to this side of the partition. Let's write that constraint. So what are the arcs that connects the city from this side of the partition to this side of the partition? x2, 1. x2, 1. What else? x2, 3. What else? x2, 6. What else? x2, 7, x2, 10, x2, 9, and x2, 10. Okay, what else? What are the other arcs that connects the city from this side of the partition to outside? That will be x4, 1, x4, 3, x4, 6, x4, 7, x4, 9, x4, 10. What else? What are the other arcs that connects the city from this side of the partition to outside the partition? x5, 1. What else? x5, 1, x5, 3. Keep going. x5, 6, x5, 7, x5, 9, x5, 10. What else? x8, 1, x8, 3, x8, 6, x8, 7, x8, 9, x8, 10. And out of those arcs, we have to have 1 in the solution. Out of all of these arcs, we have to have 1 in the solution. This is the subtour elimination constraint for this subtour. This is the subtour elimination constraint for this subtour. Okay. And this partition, our partition is 2458, 2458. Let's go to our Python code. So now it's very easy to write our subtree elimination constraints. I'm just going to copy this thing. So now our partition is 2458. Do the same thing. Look at every pair of ij's. Look at every arc xij's. If the arc is originating in the partition and terminating outside the partition, add that decision variable to the left-hand side of the constraint. But this is the subtree elimination constraint for 2458. Okay. Let's run the code and let's make sure that this subtree elimination constraint is also properly implemented. And then we're not going to look at this again. Run this code. Run. Good. Let's get our traveling salesman problem. So this is the subtree elimination constraint for the subtour 2458. So from 2, I go to 1, 3, 6, 7, 9, 10. From 2, I go to 1, 3, 6, 7, 9, 10. Is that what we want? From 2, I go to 1, 3, 6, 7, 9, 10. It's correct. From 4, I can go to again 1, 3, 6, 7, 9, 10. Is that correct? From 4, I can go to 1, 3, 6, 7, 9, 10. And likewise, from 5, I can go to 1, 3, 6, 7, 9, 10. And from 8, I can go to 1, 3, 6, 7, 9, 10. And that's greater than or equal to 1. So this is exactly the subtree elimination constraint that we wanted. Great. So then let's go ahead and add the subtree elimination constraint for the subtour 6, 7, and also for the subtour 9, 10. Let's go to our code. 6, 7. Let's give a name to that constraint, 6, 7, and 9, 10. 9 and for 10, let me just put a 0. Okay. 0 denotes the 10th node. Okay, so now our integer program have the subtree elimination constraints for the 4 subtours that we face along the way. Our integer program includes the subtree elimination constraints for these 4 subtours that we solve along the way. Okay, so now let's go ahead and solve this integer program. Run. Okay. Oh, let's also optimize and look at the solution. Good. Let's solve this integer program and look at the solution. Run. Okay. Here's the solution that we get after we added those 4 subtree elimination constraints. Let's see what the solution looks like. Let's draw that solution. From 1, we go to 3. From 1, we go to 3. From 2, we go to 5. From 3, we go to 4. From 4, we go to 7. From 5, we go to 2. From 5, we go to 2. From 6, we go to 1. Good. From 7, we go to 6. From 8, we go to 10. From 9, we go to 8. Up. And from 10, we go to 9. Okay. Good. And all the decision variables that are not printed out, they have 0 values. So that's that. Okay. So now, after we added those 4 subtour elimination constraints, do we have subtours in our model, in our solution? Do we have subtours in our solution? Yes. So now we're going to add the subtour elimination constraints for those 3 subtours. One subtour is 1, 3, 4, 7, 6. The other one is 2, 5. The other one is 8, 9, 10. Okay. So let's add the subtour elimination constraints for the first one. So the partition is 1, 3, 4, 6, 7. Okay. We keep the previous subtour elimination constraints. We still have to break those subtours. We keep the previous subtour elimination constraints. So the new subtour we saw included the cities 1, 3, 4, 6, and 7, right over here. 1, 3, 4, 6, and 7. So then here's the subtour elimination constraints for that. And then this is the subtour elimination constraint for 1, 3, 4, 6, 7. Good. And what else? We had a subtour that includes cities 2 and 5. So this is the subtour elimination constraints for 2 and 5. And what else? And we have another subtour that includes cities 8, 9, and 10. 8, 9, and 10. So our partition is 8, 9, and 10. 8, 9, and 10. Good. So let's solve this model with all the subtour elimination constraints that we added so far, and let's see what solution we get. We optimize the model and write the x variables. Run the traveling salesman example. Okay, this is the solution we get. Let's plot the solution we have. In this solution, we go from city 1 to city 3. We go from 2 to 1. We go from 3 to 4. Sorry, let me do it again. In this solution, we go from city 1 to 3, city 1 to 3. In this solution, we go from city 1 to 3. And then we go from city 2 to 1. And then we go from city 3 to 4. There it is. And then we go from city 4 to 6. City 5 to 2. City 6 to 7. City 7 to 9. City 8 to 5. 8 to 5. City 9 to 10. City 10 to 8. So this is the solution that we obtained. Okay, good. So let's go back to our piece of paper. Does this solution include any subtours in it? No. So then by adding the subtour elimination constraints that we added, we obtain a solution that doesn't have any subtours in it. So this is the optimal solution to the traveling salesman problem. This is the optimal solution to the traveling salesman problem. Good. So, but one of the interesting things is that this was a problem. We had 10 cities. That means that the number of subtour elimination constraints was 2 to the 10. So that means that we had 2 to the 10, 1024 subtour elimination constraints. But along the way, how many of those subtour elimination constraints did we add? In the first iteration, we added 1, 2, 3, 4 subtour elimination constraints. Then in the second iteration, we added 3 more, 1, 2, 3. So we added only 7 subtour elimination constraints, and that was enough to get an optimal solution to the traveling salesman problem. Okay, so out of those 1024 subtour elimination constraints, it was enough to add only 7 of them to get to the optimal solution to the traveling salesman problem. So then, the cool ideas that we learned today is in the formulation of the traveling salesman problem, we have so many of these subtour elimination constraints, but you can have a problem formulation where you have so many of these subtour elimination constraints, namely like 2 to the n of these constraints. And when we're dealing with an optimization problem that has too many constraints, but a manageable number of decision variables, when we're dealing with an optimization problem that has too many constraints, but a manageable number of decision variables, what we do is, like for example, here, when we're dealing with an optimization problem where we have a manageable number of decision variables, but too many of these constraints, we say, well, solve the problem without too many of those constraints, and check if the solution that you get, check if you got lucky, check if the solution that you get without imposing these constraints actually satisfies these constraints. If the solution that you get without imposing those constraints satisfies these constraints, then we're done. There's nothing else to do. But more likely what's to happen is if you solve this problem without imposing these constraints, you're going to get a solution that violates some of these constraints, add the violated constraints, and then solve one more time. Okay, so it's an idea of iteratively adding these large number of constraints one by one, and along the way you check whether you violated any of these large number of constraints, and whenever you find any one of these large number of constraints violated, you add them those as well, and eventually you're going to get a solution that's not going to violate any of these constraints, and you're going to get to the optimal solution. Okay, so this is the formulation of the traveling salesman problem, again, which happens to have 2 to the n constraints of this form, but there is nothing to be scared of. We can gradually add these subtermination constraints and still get to the optimal solution to the traveling salesman problem. Okay. We can go into the wrap-up mode. The formulation of the traveling salesman problem was a little tricky. If you had n cities, we had 2 to the n subtermination constraints. So that's something interesting. And whenever we deal with problems that involve routing, you could be routing garbage trucks, multiple garbage trucks throughout the city. You could be routing multiple traveling salesmen through different regions of the city and so on and so forth. These kinds of subtermination constraints always pop up. So this is something that is useful to know. And the number of subtermination constraints can be daunting, but there is nothing to be scared of. So you solve the problem first without any subtermination constraints, and see if you get lucky. If the solution without any subtermination constraints does not have any subters in it, we're done. But more likely, again, what's to happen is without any subtermination constraints in the formulation, we're going to get a solution that violates some of the subtermination constraints. Then we add those subtermination constraints and solve the problem again. See if that solution violates any subters. See if that solution has any subters. If it does, then you add the subtermination constraints for those subters that we face along the way. So we add the subtermination constraints gradually. This is a neat algorithmic idea. Good. So let's stop here.